Hello and welcome to this webinar that will provide an introduction to mixture design. My name is Lennart Eriksson and I am part of Sartorius STEM Data Analytics. We are a business solution provider inside the field of advanced data analytics, and our solutions are realized through the so-called geometric suite. The geometric suite comprises the software elements MODDE for design of experiments, Easy Analytics for univariate process analysis, SIMCA for multivariate data analysis, and the online extensions called SIMCA Online Control Advisor and Active Dashboard. And what we will discuss today takes place in the MODDE software for design of experiments and quality by design. Here we have a little overview of today's presentation. We have an introductory segment where we will walk over what is the difference between what we call process experiments and mixture experiments. And we will also see what we can do when we have process and mixture factors varied at the same time. We have a middle section where we will have a walkthrough of a classical mixture design. And for those of you that have attended some of our DOE trainings, you will recognize the tutorial dataset called Rocket. We will look at the data analysis and the interpretation of the resulting model. The second example is an example where we are at the same time involving both process and mixture factors, and we will illustrate this scenario using our tutorial dataset called Bubbles. We will have a complete walkthrough of that example, all the way from setting up the experimental design to the final data analysis. There will also be a little demonstration session where we will actually demonstrate both these data sets inside the MODDE software, and towards the end there will also be some summary and concluding remarks. So I think it's fair to say that the most common application of design of experiment involves investigations where so-called process factors are studied. And the DOE protocols that are used in conjunction with process factors, they contain experiments in which the response Y is a function of the levels or the amounts of the factors. And in other words, that means that the changes in the levels or the amount of each factor are not coupled to changes in the other factors. It means that they are independent of changes in all the other factors. And in this context, common DOE protocols that we are using are drawn from the factorials family, fractional factorials family, and Plackett-Berman designs for screening, and for instance the central composite designs when it comes to optimization or response surface modeling. But of course there are also other experimental families that apply when we are dealing exclusively with the process factor. And on the next slide, we see a couple of examples of what the design region might look like when we deal with process factors, and in this case using screening DOEs. So the main point is that if there are no external restrictions on the investigation ranges of the factors, well, then the experimental domain can be understood to a regular cube or hypercube, or possibly maybe a half hypercube, depending on how many factors are studied and which explicit experimental design is chosen. Then on the next slide, we look at the other main type of application of DOE, which involves so-called mixture factors or formulation factors. Then we have DOE protocols that contain experiments where the response Y is a function of the proportion of the ingredients in the mixture and not the amount or the levels of the ingredients. So when you change the proportion of one ingredient in the mixture, you cannot freely change the proportions of any other ingredient in the mixture. And the reason for this is the so-called overall mixture constraint, which implies that the sum of all ingredients in the mixture is 1.0 or simply 100%. And because of this constraint, we can express the relative proportions as fractions or percentages. And when we deal exclusively with mixture factors, the experimental domain is no longer interpretable as a cube or a hypercube, but becomes interpretable as a simplex or a triangle or a polyhedron. And the important thing to realize is that the experimental region has the dimensionality 1 less than the number of mixture factors. So if we have k mixture factors, the experimental design, when we deal exclusively with mixture experiments, has dimensionality k minus 1. But of course, we don't have to have designs where we study process factors separately and mixture factors separately. Of course, we can also handle them in one and the same protocol. And depending on the perspective we choose, we can render such combinatorial or hybrid designs using different representations. And yet another level of complexity is then introduced when there are constraints in the experimental space. Here we see constraints exemplified in the context of process factors, and we see constraints in the context of mixture factors. And when we have constraints, well, in such a case, the experimental regions are irregular regions, and such complicated DOE cases unavoidably imply a need for the use of a so-called D-optimal design. A D-optimal design is a computer-generated design. It needs an algorithm, and the details of what the D-optimality means and D-optimal design means is discussed in a separate webinar, and I refer to the recording of that webinar for more details. We have now come to the second stage in this presentation, where we will look into the two applications, and we will start with the Rocket dataset, in which we have mixture factors only. So the objective here was to blend three components in a mixture: the binder, the oxidizer, and the fuel, in order to form a rocket propellant. And the purpose was to find a propellant with an elasticity exceeding 2,900. And you can see that the three formulation factors in this case are not varied between 0 and 1, but have modified bounds. So the binder is going to be varied between 0.2 and 0.4, oxidizer between 0.4 and 0.6, and fuel between 0.2 and 0.4. To the right on the slide, we see the resulting experimental worksheet, and we can see the elasticity that has been measured given the different combinations of the three formulation factors making up the propellant. And the hallmark or the characteristic feature of a mixture design is that the sum of all the ingredients in the mixture will be 1.0. And that has certain consequences then for the experimental design. On this slide, we are overviewing what the mixture design region will look like when we have three mixture ingredients in the mixture, and the triangular shape would arise if all three ingredients would be allowed to vary between 0 and 1. Now in this case we have different boundaries, but we can still see that we are having a regularly shaped experimental region, although it is a smaller fraction that we're investigating of the total available experimental domain. And in the next stage, the data analysis stage, we would like to see if there are any relationships between changing proportions of the three mixture factors in the mixture and the measured changes in the elasticity response variable. And when we are analyzing data in a mixture design, we follow exactly the same workflow as compared to when we are analyzing experiments arising from the work with only process factors. So we will use the analysis wizard in the MODDE software in exactly the same way as for any other type of DOE investigation. The only little difference is that when we are evaluating the results in terms of contour plots, we will have in the mixture case a so-called trilinear contour plot. And we can see here that the model predicts an area in which the elasticity exceeding 2,900 is found. The other little difference relates to how you interpret the regression coefficients and model modification possibilities. The coefficients are interpreted in a very similar way compared with the regular DOE protocols, but the coefficients are connected together, which means that editing a model when you're doing mixture design becomes slightly more complicated. In this case, the coefficients show that binder and fuel have the strongest impact on elasticity, and having more fuel and less binder is beneficial for obtaining a higher value of the elasticity. Now, as our second example, our intention is to outline how process and mixture factors can be combined in one design. Now, the background to this application is that the presenter of this webinar was on paternity leave with his older son in the late 90s. And one day the son got a soap bubble mixture and a wand from one of his older cousins. But at this point in time, the son was simply too young to understand how to blow bubbles and use the equipment. But the bored father on paternity leave was not. So the bored father started blowing bubbles, and because the resulting bubbles initially bursted too rapidly, the father started making experiments with the bubble mixture composition. And so it was decided to use the mixture design approach for investigating which factors affected bubble formation and lifetime. So we browsed the internet looking for a suitable bubble mixture recipe, which we could use as a starting reference mixture. Then this recipe was modified using mixture design, and bubbles were blown for each new mixture. There were 4 ingredients in the mixtures. There are 2 dishwashing liquids or washing up liquids, tap water and glycerol to give the mixture some viscosity. In addition to these restrictions, there was also a so-called relational constraint specifying that the sum of the washing up liquids ought to be between 20 and 50% all the time. We also had 2 so-called process factors, which was the temperature of the bubble formation when blowing the bubbles, either a refrigerator-cooled solution or a solution that had been standing in room temperature. In addition, it was also the time from the mixture settling time from the mixing until blowing the bubbles. And we were then measuring a response, which was the lifetime of the bubbles in seconds obtained when blowing the bubbles, and the time until bursting was measured for bubbles of around 4 to 5 centimeters size. And the specification that we were opting for was trying to get bubbles lasting for at least 60 seconds before bursting. We can see on the next slide a little overview of the design region in the bubbles example. So we have chosen to have the 2 process factors, time and temperature, as the reference basis, and then at each combination of time and temperature we then have the changes in the bubble mixture composition. This is a somewhat simplified representation. When you're doing DOE in the next stage, you have to select which experimental objective and mixture model you would like to work with. We selected experimental objective screening because this was an initial assessment, and in order to limit the number of experiments required, we took a not overly complicated model. So the full model is seen down here. It has an interaction between time and temperature, only linear terms among the mixture factors, and then interactions between the process and mixture factors. Now, before moving in and looking at the details of the experimental protocol that was generated in the bubble mixture example case, I want to dwell on a moment on something called the reference mixture. The reference mixture is used for anchoring the mathematical model. It is easy to find for regular mixture regions. It is simply the overall centroid. But when you have strongly irregular mixture regions, you need an efficient algorithm to find the centroid. The reference mixture serves the same function as the center point in the process design. It means that the regression coefficient relate to changes from that point. In the current example, the calculated reference mixture had this composition, in turn and order for the 4 ingredients, the 2 washing up liquids, water and glycerol. Due to the fact that experiments were made in a non-high-tech kit, it was manually modified to become this. And here we have the proportions for the 2 washing up liquids, water and glycerol. So it means that later on in a couple of slides when we're looking at the coefficients for the different ingredients in the mixture, any coefficient will relate to this composition of the reference mixture. Here we see the worksheet with the response data. We have generated a D-optimal design, and again I refer to a separate recorded webinar to give you the details of the D-optimal approach. The best design had 16 experiments with a G efficiency of 76% and a condition number of 2.7, which are very, very good statistics for a screening mixture design. In addition to the 16 experiments, we also added 2 series of 4 replicates. So the bottom 8 experiments, or the bottom 8 rows, represent these 2 times 4 series of replicates. So the total experimental design had 24 runs. And it's quite interesting to see that there is a rather large span in the lifetime measured across these 24 experiments. The shortest lifetime was 11 seconds, whereas the longest lifetime before the bubble was bursting was 362 seconds, or 6 minutes and 2 seconds. We will now try to see how changes in the 2 process factors and changes in the mixture composition is correlated to this lifetime response. And we will do the data analysis in terms of the guided workflow represented by the analysis wizard inside the MODDE software. The first stage in the analysis wizard is the so-called replicate plot. And the replicate plot will show how replicated experiments change numerically in relation to changes across all experiments in the experimental plan. And of course, the ideal result is that you have small variability among the replicates compared to the variation across all experiments in the design. And we see here that replicates, that means experiments with this exactly the same combination of the factors, are concatenated by a line and also given a blue color. And in this case, we have a very small replicate error, so we understand we have good data, good input data to work with. The second plot in the analysis wizard is the histogram plot, and the preferable shape to the response variable is close to a normal distribution. And in this case, we have applied a logarithmic transformation to the lifetime data in order to mimic an approximate normal distribution. We can see that there is a small tilde symbol, or a half-lying digit number 8, that has been appended to the name, and that is a little indication by the MODDE software that this response is being logarithmically transformed and analyzed in the transformed metric. In the next stage, we are looking at the model, and here we see the coefficients for the initial model, and the insert shows the summary of fit statistics. We have a rather high explained variance, or R square, but a rather low Q square, or predicted variance. And this rather large gap between the R square and the Q square points to some imperfections in the model. And as we can see, there are a number of the higher order terms that are close to 0. So on the next slide, we are seeing the result of revising the model and only working with the linear terms of the model. And you can see how the model becomes much more stable, evidenced by a sharply increasing Q square and also dramatically decreased confidence intervals on the coefficients. So this is our optimal model, which we're going to exploit in the coming slides. Another quality check of the data and the model consists of making a normal probability plot of residuals. And without complicating things too much, you can say that what we are looking for here is that all the points, all the residual points, neatly line up on a diagonal band like this. And ideally, we should have, when we are eyeballing and fitting a line to the points, obtain a line which will go through the anchoring point, 0 residual and 0.5 probability. So again, we have an indication of a very good model, because there is no systematic structure to the residuals, which is the desirable pattern. The last plot inside the analysis wizard is the so-called observed versus predicted plot. So we see the observed lifetime versus the predicted lifetime in the logarithmically transformed unit. And we have a very good agreement between measured lifetime and predicted lifetime. Once we are exiting the analysis wizard and start to make plots of the contour plot type or the sweet spot plot type and so on and so forth, we will be working with cases where the response has been back transformed. So outside the analysis wizard, we are looking at representations where all the results have been back transformed to the original unit, the second unit, so to say, for the response. Here we see an array of 3x3 trilinear contour plots that we can obtain when we are changing temperature and time. So this is the temperature scale, 7, 14, and 21 centigrades, and this is the time scale, 1, 13, and 25 hours. These 9 trilinear contour plots have a consistent color coding across them, so it means that wherever you have a blue field, you have the same predicted level of the lifetime. So what we would be looking for is the largest orange or red area. That would be the most promising region for having long-lasting bubbles, and that would be in the top left-hand trilinear contour plot in the segment where I'm pointing right now. Beyond the trilinear contour plot, we can also use the optimizer of the MODDE software, trying to propose verifying experiments. And we will see the optimizer come into play in the demo shortly. So the MODDE optimizer was used to propose 2 verifying experiments. And when performing these verifying experiments in reality, we measured one lifetime of 18 minutes and 40 seconds. And in the other case, the bubble had a lifetime of 13 minutes and 30 seconds. So we obtain strong evidence that through the model interpretation and through the use of the software optimizer, we are able to identify interesting directions in which to move along in order to improve the result even further. That is, in this case, to get soap bubbles of even longer lifetime. This brings us over to the section where we're going to demonstrate the MODDE software and how easy it is to accomplish mixture design inside the MODDE software. We will start by demonstrating the rocket experiment, and after that we will also look into the second case of the bubble formation dataset. The first step is then to define the problem, and that we can very easily and quickly do using the design wizard. So we are going in to the design wizard, and the first stage is then to define the factors or the formulation factors. The first factor is the binder. It is a formulation, and the low bound is 0.2 and the high bound is 0.4. We then click add another, and the second mixture factor is the oxidizer, which is investigated between 0.4 and 0.6, and the third factor is the fuel, and the fuel is studied between the low bound of 0.2 and the upper bound of 0.4. Now we say OK because we have defined the factors. We then click next to proceed to the next stage in the design wizard, and that is where you can define the one or more responses. In this case, the response is the elasticity, and the requirement is that it should exceed a minimum value of 2,900. Now we have input factors and responses, and we click next to proceed in the design wizard, and we are now at the stage where we would select the experimental objective. The experimental objective can be one of screening or optimization, irrespective of whether we are working with mixture factors alone, process factors alone, or any combination. In this case, in the rocket example, the objective was optimization, and when we then proceed, the MODDE Pro 11 software will provide a list of all the eligible mixture designs that have a good chance or probability of solving the problem. And the different models will be listed in the order of which sort of regression model they are supporting. MODDE will always have a first recommendation and a second recommendation. These are designs that are well apt for the problem at hand and not encoding an overly high number of runs and not an overly complicated regression model. And in this case, the first recommendation is an experimental design, a classical mixture design called modified simplex centroid that has 9 runs. And MODDE also proposes to make 3 replicates, so a total of 12 experiments, you can say. And this is the design that was done in reality. So when I'm clicking finish, we are leaving the design wizard, and here we now see the experimental design. I will now go into Excel very quickly and fetch the response date, paste them in to the Y variable. So now you can say we have completed all the steps of the so-called design wizard, and we may now proceed to the analysis wizard. And in the analysis wizard, we then have this guided workflow. I will enlarge this window a little so we see where the first plot is the replicate plot. And we can see that the spread in the replicates is small compared with the spread across all the other experimental points. The histogram plot of the elasticity suggests that we should continue to work with the response in the untransformed metric. The model performance statistics show somewhat of a gap between the R square and the Q square. Usually we would be more happy with better harmonizing or smaller differences between the green and the blue bar, but we have to proceed to see what this arises from. Here we see the regression coefficients, and now remember that they all depart from the combination of the overall centroid in this case. So we see that decreasing binder in the formulation and increasing the proportion of fuel in the formulation would encode a larger or a higher numerical value of the elasticity response. Now, if we, for instance, would like to modify the model by dropping some small regression term, then MODDE will start to issue warnings because, as I told you, the mixture, the terms of the mixture model are combined like links in a chain, and you have to treat them as a conglomerate of terms. You can't take away a certain term in isolation, and MODDE will always keep track of how the terms are linked to one another and issue different warnings depending on which term you're trying to remove. And for this reason, usually the model revision in mixture design is more difficult, and maybe also sometimes you would not even do that because of the complexity, the complex relationships among the terms in the regression model. And in this case, we are not going to do any model revision. We will live with the model we have, and that also means we conform to the model presented by the original investigators. The next plot in the in the analysis wizard is the normal probability plot of residuals, and we can see that one of the experiments that is tricky is the experiment number 4, and this is also the one that deviates mostly in the observed predicted plot. So here we would definitely, if it would be possible to make more experiments, retest number 4 to see if it would persistently be down here. It could be that there is a deviation, experimental oddity when this experiment was performed. Another reason could be that we are simply using a too simple regression model, and maybe a special cubic or a cubic model would pick up this deviation. It's hard to know without being able to make follow-up experiments. Upon clicking finish, we are exiting the analysis wizard, and we are now at the stage where we can use our model, and we can make contour plots, we can make sweet spot plots, and we can make design space plots. And I will only exemplify the contour plot. We're proceeding here. We only have 3 mixture factors, so there aren't any choices to make regarding which factors are to be plotted. And here we then see the resulting trilinear contour plot, which is the same one as I was presenting in the PowerPoint part. So after having looked at the main workflow of the MODDE Pro 11 software using this rocket propellant example, we're going over to the bubble mixture experiment, and I will now jump in a bit into the story here, the storytelling. We have defined our 6 factors. We have defined the lifetime of the bubbles in seconds, and it's log transformed, and here we have all the experiments. So basically we are now entering into the story when we will go into the analysis wizard. We start the analysis wizard, and again we have the same sort of workflow or order of plots as we had in the previous example when we went through the rocket propellant example. So first we have the replicate plot, and here we have the histogram plot of the lifetime, and it is now logarithmically transformed. I can actually just show you by clicking on the transform button what the histogram look like by remove the transformation. And this is what the histogram would look like for the untransformed response. So it's definitely so that a transformation is something you should look into. And you can also compare the stability of the model when you're making a model on the untransformed response as opposed to the logarithmically transformed response, that the model actually stabilizes just from that very, let's say, simple measure. Here we have the summary of fit plot. When we come to the coefficients, we see that there are a number of coefficients that are small and that can be removed, and that can be done interactively by selecting the so-called exclude tool. I do like this, and the model is updated on the fly, and now you see the statistics for the improved model. The next plot is the normal probability plot of residuals, which looks very nice. And here we have the observed versus predicted plot. We can now make different types of contour plots in the same way as we did the contour plot for the response in the bubble formation example. But what we'll do now is actually demonstrate the capability of the optimizer. So I will start the optimizer. I will just make sure that I have zeroed everything. The MODDE optimizer is an automatic search algorithm that will or search functionality based on a desirability function and simplex optimization that will automatically search through a myriad of factor combinations, trying to locate a combination of factors, the so-called set point, that encode a predicted response value that is in line with specification. And the specification here is that we should exceed, we should maximize the lifetime, but we should definitely exceed the minimum of 60 seconds. So when I click Run Optimizer, it will start as many as 20 simplexes, addressing the response from different parts of the factor space, you can say, and it will then present at convergence the results in terms of 2 statistics. It will contrast the different set points based on a logarithmic distance to the target, and it will also contrast the performance of the different alternative set points from a parameter called DPMO, defects per million opportunities. How many predictions in 1 million predictions will violate the specification of exceeding a lifetime of 60 seconds? So you can select any one of these set points, and you can see how the factor combination of that particular set point is changing, and also how the predicted value is changing. All these 20 set points that are also detailed in the alternative set points tab, they are mathematically optimal in some respect. So often the mathematically optimal set points have factor values that are relatively close to the maximum or the minimum settings for the different factors, or
with regards to the mixture factors to the upper or lower bound, giving very little room for flexibility if you have a problem of regulating or upholding a certain value of a certain factor. So for that matter, we often search for a robust set point. So the robust set point is something that will have some margin to the factor borders, and if a robust set point is found, it will be added to the list of eligible set points using the notation R. So we can see here the combination of the different factors when we are using this robust set point search, and the DPM of 700 indicates a very low risk of failing to comply with the specification of exceeding a lifetime of 60 seconds. Only in 700 predictions out of 1 million do we have a violation of the specification. We can also use a plot called the design space plot, showing where the robust set point is located, and we will center the plot around the factor definition. It is the lifetime, and we will also just make sure that we have the different resolutions here. So we will now search across different combinations of the factors in this problem, calculate what is the DPMO, the risk of failing to comply with the specification, and visualize the result in terms of a trilinear contour plot. And in this so-called design space plot, the color coding is now not anymore according to the contour levels is not anymore according to the predicted lifetime in seconds. The contour levels represent the risk of failure. So where the green color starts, there is 1% risk of failing to comply with the specification, meaning that 10,000 predictions in 1 million predictions are violating the specification. They would be lower than 60 seconds. And the coordinate which was found to be the the robust set point is now indicated by the crosshairs symbol. So there is definitely a rather large green region which we could call a design space, where there is a very small risk or low risk of violating the specification of a lifetime of 60 seconds. You can see that the contours of the surface that is plotted are relatively rugged, and also that the contour lines are a bit wiggling, and that has to do with the resolution that is used when calculating this plot. I was running on a low resolution of 64 just to make the calculation not last overly long. But it is of course possible to run on a much higher resolution, and I have prepared such a plot, and you can then see how much more smooth the borders of the colored area is. So this was running using a much higher resolution, but then the calculations took like 30 minutes or so. But like a good chef, I have prepared this, so you can obtain smoother results if you do more rigorous calculations at the end.
So with this little demonstration of the MODDE software and its capabilities for performing mixture design, we're now moving over to a short rounding off session inside using some concluding remarks. So in summary, what we have said is that design of experiments is an organized approach. Through a well-planned DOE protocol, you always yield more useful information because you can map the influence of all factors on the one or more responses at the same time. You yield more precise information in fewer experiments, and we are always evaluating the results in the light of uncertainties and variabilities. Think, for instance, of the regression coefficient plot, where we superimpose the precision on each coefficient in terms of the confidence interval. And we are very much geared for trying to represent our results as maps, in this case trilinear contour plots that are useful for obtaining a system overview and also making decisions, concrete decisions of what to do next. Regarding specifically mixture design, the characteristic feature is that all ingredients sum up to 100%. That means that all formulation factors cannot be manipulated freely of one another. So, and therefore there is also a change to the shape of the experimental region. The experimental region can either be a regular or irregular simplex, depending on how the restrictions or the bounds of the different formulation factors are specified. Apart from that difference with regards to the shape and geometry of the experimental design, or the experimental region, I should say, the approach to mixture design is very similar to the approach used for conventional process designs. So we have the same guided workflow in terms of the analysis wizard, and that approach was also discussed in the PowerPoint slides. So all in all, we can say that the approach to mixture design is very easy in MODDE Pro 12. It is easy to generate mixture designs, it is easy to analyze the mixture designs, and it's easy to communicate the results arising from mixture design. And with these words, I would like to thank you all for your time and attention. I hope you find this presentation a useful one. Thank you very much.